Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for coming. Today it's our pleasure to have Abhigan Sharma from UMass. Abhigan is finishing his PhD with Arun, and he has done some very interesting work on infrastructures for content distribution networks, and also some work on mobility and stuff. So, Abhigan.
Hi. Thanks for the introduction. I'm Abhigan from UMass, and I'll be talking about why geo-distributed internet services must get their content placement right before anything else. So let's start by looking at how our computing infrastructure is going to look like in the future. Today, cloud computing platforms with tens of data centers are pretty common. Now, these geo-distributed platforms are important because propagation delays on the internet are fundamentally limited by the speed of light. Now, having a data center close to the user reduces propagation delay, leading to an improved performance. Now, given the importance of geo-distribution, it is entirely feasible that in future we may see computing platforms with hundreds or even thousands of locations. Besides data centers, other forms of computing infrastructures can emerge. For example, set-top boxes, cellular base stations, and routers are all being discussed as potential avenues for running general-purpose computation. And in future, we may see these devices being used for them. Now, so it's possible that in future, our infrastructure is going to be more geo-distributed and possibly heterogeneous as well. Another trend that's already common and is going to become probably more common in future is the network mobility of endpoint principles, such as interfaces, devices, internet-connected things, content, and services. Now, network mobility presents a challenge to establishing end-to-end communication because it changes the network location of an endpoint. Now, there are several examples of network mobility. A user, Alice, who's initially at work and has a particular interface on Wi-Fi and cellular, when she reaches home, she may have a different interface on these, different IP address on these interfaces. Similarly, a file stored in Dropbox may be on a server in one data center, but over time it could get moved to a server in another data center, thereby changing the network location at which the particular content is available. So given these projections about how our computing infrastructure is going to look like in future, my research vision for future internet services comprises of three main elements. First, we'll need geo-distributed services that leverage the geo-distributed resources that are potentially heterogeneous as well. Second, we'll need services that enhance our ability to handle the mobility of endpoint principles. And third, we'll need meta services that automate the deployment and reconfiguration of these geo-distributed services. Now, in my work towards realizing this vision, in this talk, I'm going to talk about two things. First is a geo-distributed service, which is a network CDN. And this is a content delivery network that's deployed by an internet service provider. From the core of the network, we'll move on to the endpoints, and we'll see how Auspice Global Name Service enhances our ability to handle the mobility of these endpoints. Now, a key focus of this talk is geo-distribution. And so let's start by looking at what are the advantages geo-distribution brings in terms of the degrees of freedom. So in the simplest case, when resources are at one location only, the degree of freedom we have is that of choosing the underlying network routing from the end user to the data center where we are located. On the other hand, when your resources are geo-distributed, two additional degrees of freedom come into play. First is content placement. That is, selecting the locations where content is placed. And second is request redirection. That is, among the multiple locations that have a content, which copy of content should a particular request be sent to? So 3 degrees of freedom: placement, redirection, and routing. So let's start with network routing first. Now, network routing, or traffic engineering, is a problem that's commonly solved by ISP, internet service providers today. And a simple view of this problem is as follows. The input is a traffic matrix, and the ijth entry in this matrix represents the traffic demand from a node I to another node J in the network. Now, based on this traffic matrix and the link capacities of links in the network, traffic engineering outputs network routing, or the set of physical paths between all nodes in the network. Now, these traffic engineering functions typically optimize network cost functions. And these cost functions are defined in terms of, are typically convex functions of link utilization. For example, a common cost function is the maximum link utilization. So why is the utilization of links important? That's because a low utilization of all links implies that network is free from congestion hotspots and has more spare capacity. Now, a simple example can show how traffic engineering reduces this link utilization. So on the left, we have a shortest path routing, and we send 2 Mbps of traffic from node A to node B. You send this via the bottom link because it has more capacity. And this gives an MLU of 2/3 or 0.67. On the other hand, if we are a bit more smart about the routing, we can split this traffic between the top and the bottom link, which gives a smaller MLU of 0.5. So a smarter routing can reduce link utilization and network cost. Now, among the 3 decisions, placement, redirection, and routing, it is content placement that's perhaps the most important to leverage the power of geo-distribution. So let's start with redirection first. Now, the objective of redirection is to select a location to which to send requests among the ones that have the content. But if your content is placed only at a faraway location, then irrespective of how you do redirection, an end user is going to observe high latencies. On the other hand, content placement can create more options for the redirection scheme to choose a location that is nearby. So let's consider placement versus routing. Suppose we need to compute routing for this traffic matrix. The flexibility of placing content is so powerful that it can change this traffic matrix itself. Now, if all the content that a node in the network wants is placed at the same node, now in that case, there's no need to send traffic to any other node. And all the entries in this traffic matrix turn to 0. So there's no routing problem to be solved. Now, this is clearly an extreme example, and you may have resource constraint on what you can place at a location, but it demonstrates the power of placement over routing. So with this introduction to placement, redirection, and routing, let's see how these play out in the case of a network CDN. Now, this is new and relatively new and a potentially transformative change in CDN landscape. The traditional tripartite view of content delivery has 3 sets of entities. Now, you have content providers who produce content, internet service providers who provide network connectivity, and a CDN which delivers content via an overlay network of servers. Now, in more recent times, ISPs have started to deploy CDN functionality as part of their infrastructure, giving rise to network CDNs or NCDNs. So why are these ISPs interested in NCDNs? So one reason for this is the rise in internet traffic, especially video traffic. And ISPs see NCDNs as a way to leverage content caching to reduce traffic on their backbone and reduce the cost of provisioning network capacity. Another major motivation for ISPs is to monetize these NCDN service, for example, by selling an on-demand video service to the end users. Today, 30+ NCDNs are there, including some of the biggest telecom providers in the US, including AT&T and Verizon. And this number is expected to grow because CDNs have started offering the technology to ISPs to deploy these NCDNs. So NCDNs are potentially a game changer for the CDN industry. And in this talk, we'll see why managing an NCDN is a different problem from managing a traditional ISP or a traditional CDN. So before we go there, let me quickly go over the abstract model of an NCDN that we work with. So we have points of presence, or POPs, of a network CDN, which consist of backbone routers, as well as content servers that deliver content to end users. Additionally, we model origin servers that are maintained external to the NCDN, and they can be reached via a few exit nodes that connect to the origin. The origin acts as the source of all content. When an end user makes a request, it first goes to the nearest POP. If the content is available there, sent to the user. Otherwise, the content is fetched from any other POP inside an NCDN and sent to the user. If it happens that the content is unavailable inside the NCDN, it is, of course, fetched from the origin and returned to the user. So based on this network CDN model, we pose the following NCDN management problem. Now, to our knowledge, we are the first to pose this question where a single entity handles all three tasks: placement, redirection, and routing. And the main difference from the traffic engineering problem is that the input here is a content matrix. And the ijth entry in this matrix is the demand for a content I at a node j. So based on another two inputs are the resource constraints that we have, which are the link capacity and the storage capacity that is available at each point of presence. We also have an input on the content size vector, which represents the size of each content in the content matrix. And the output is a set of variables that define placement, redirection, and routing. Now, a natural question is to ask, okay, why are we trying to make these three decisions together? Why not we solve these problems independently? And the reason is that these decisions interact in case of a network CDN. And this interaction between placement and routing illustrates this. So suppose that's our network. And we have a content that's placed at, say, one of the nodes in the network C, with a demand of 1 at node A and 0.5 at node D. Now the question is, how do we serve this demand to minimize the maximum link utilization? The optimal solution turns out to be follows, which gives an MLU of 0.5. Now, in order to achieve this MLU, you need to use a flow split routing, which splits traffic from C to A among the two paths CBA and CDA. Now, unlike the traditional ISP model where the ISP has no control over content placement, an NCDN has the power of placing content. So let's say an NCDN uses this power to also place the content at node B. Now, in this case, it's easy to see that the MLU reduces to a much smaller value. And moreover, we can use a simpler, shortest path routing to achieve this minimum MLU. So this example illustrates the sophisticated interaction that happens between placement and routing in an NCDN. And it is to leverage these types of interactions that we define the joint optimization for NCDNs. And joint optimization works as follows. First, we measure content matrix all over the NCDN. Joint optimization runs as a centralized computation. Its output, placement, and redirection are fed back to the content servers. And the network routing is configured at the network routers. Now, we have shown that this joint optimization problem is NP-complete and is inapproximable to within a constant factor. Hence, how do we solve this? So for that, we defined a mixed integer program, formulated a mixed integer program, and solve it using a standard mathematical programming solver. This mixed integer program optimizes a cost function with subject to constraints on link and storage capacities. And the mixed integer program cost function could be a traffic engineering related cost function such as MLU, or a cost function dependent on user perceived latency. Now, we use this joint optimization to define a planned approach for managing an NCDN. To understand this approach, let's divide time into equal length intervals and consider a particular time interval, T. Now, we use CMT to denote the content matrix in that time interval. And we use PRRT to denote the placement, redirection, and routing in that time interval. So the planned approach uses CMT minus 1 to compute PRRT. That is, it uses the content matrix in the immediately preceding interval to compute the decisions for the next interval. Now, this is a realistic way to do joint optimization because it uses only previously observed content demand. Now, we have also defined a scheme, Oracle, which has future knowledge of content demand. And that scheme uses CMT to compute PRRT. Now, Oracle is clearly unrealistic to implement because you may not have perfect knowledge of future content demand for all content. But still, Oracle is useful to benchmark the performance of the other schemes. Now, this planned approach is not that simple to implement. First, it requires fine-grained measurement of content matrix in each interval. And moreover, it requires solving a potentially expensive mixed integer program that becomes intractable for large problem sizes. Therefore, we have also considered some simple unplanned approaches. And these approaches require no measurement of the content matrix and use simple heuristics for placement, redirection, and routing. So for placement, it uses simple LRU caching at each node. It redirects each request to a location that is closest in terms of hop count distance and has the available content. And for network routing, it uses a static shortest path routing in which link weights are configured to be inverse of link capacities. And this link weight setting is the default configuration for shortest path routing protocols in commercial routers. And next, I'm going to present some results which compare this unplanned approach with the planned and the Oracle approaches for real network topologies and real content access traces. So we collected content access traces from Akamai, the world's largest CDN. The data contained data from 7 million users who downloaded more than 1,400 terabytes of data. And the result shown here is for the network topology of a tier 1 ISP in the US. The y-axis in this curve is the network cost function MLU, and x-axis is storage ratio. So we are operating in a constrained storage regime because if we have infinite storage, then we can place probably all content at all locations. So not much problem to be solved there. And now what we see is that as storage ratio increases, content can be placed at more and more locations in the network. So traffic on the network link reduce, which reduces the maximum link utilization. Now what's surprising is that the planned joint optimization actually has a 3x higher MLU than the simple unplanned approach. So why is this so? The reason is that there's a lot of change in content popularity even on a daily basis in the real content workloads, and a lot of requests are for new content that's published that day. The planned approach makes this decision based on content matrix for the previous day, and so it often does not have the content placed inside the network. It needs to fetch this content from the origin, which increases the utilization of the network links and increases the MLU. Now we have also considered several other variants of this planned approach, which vary the duration of the content matrix, the frequency at which the planned approach is implemented, and combined planned with unplanned approaches. But still, the planned approach performs worse than the unplanned approach in those experiments also. So that's one. The next thing is that the simple unplanned approach actually performs pretty well and has a network cost. The difference is actually 18% at storage ratio of 4. So why does the unplanned approach perform well? The reason is that its placement strategy, LRU caching, is actually pretty good. Now, due to locality in real-world workloads, what we see is that its cache hit rates exceed 90% in some of the cases. So it's effective in placing content inside the network, which reduces the network cost and leading to a good performance. So the high-level takeaway from this graph is that content placement matters tremendously in network CDNs. The planned joint optimization performs poorly because its placement strategy is ineffective in placing content in the network. On the other hand, the unplanned approach works well because its placement LRU caching achieves good cache hit rates. So a natural next question is to ask, how much does network routing matter in network CDN? Yeah, sure.
Does the network cost for the unplanned case also include the fetches of the content from the origin servers?
Yes, we do account for that cost for all schemes. So even when planned approach goes from one configuration to the other, there's a cost of content movement, and that is also accounted for. So how much does routing matter? And to answer this question, we considered our basic unplanned approach with static shortest path routing, which is a scheme that does traffic engineering. That is, it optimizes routing based on previously measured traffic matrices. And the y-axis in this curve shows the maximum reduction in MLU that traffic engineering achieves over the static shortest path routing across all storage ratios. And x-axis shows the results for the various traces. Now we find that the maximum reduction in MLU is 10% or less, which suggests that optimizing routing gives only a small cost reduction in network CDNs. So based on these two findings, our overall takeaway message to network CDNs are as follows. First, network CDNs should keep it simple because a realistic joint optimization actually performs worse than even simple unplanned schemes such as LRU caching and static shortest path routing. And moreover, the unplanned approach performs close to the ideal at higher storage ratio, suggesting that there's only a small room for improvement over the simple unplanned approaches. The second message is that content placement matters more than routing in network CDNs. It matters more where you place the content in the network and matters less how you route to that content.
Does this kind of translate to that there's not a real point for doing network CDNs? In the sense that effectively the findings suggest that operating the networking, operating the CDNs independently is more or less close to optimal.
Yeah, that is true, but it doesn't. Operators still have a motivation for network CDNs because if they have the CDN service, A, they can have a wider deployment in their network, and B, if they have it, they can make money by selling the CDN.
They can operate it as completely separate.
Yeah, they can operate, yes. So you do not need joint optimization. Yeah. So simpler approaches work well. Okay. So from the core of the network, we'll move now to the endpoints, and we'll see how Auspice Global Name Service enhances our ability to handle these mobility of these endpoints. Now, let's start by looking at the state of affairs for mobility in today's internet. Today, it is difficult to initiate a general purpose communication with a mobile device because there's no global infrastructure to locate it. Now, as a result, mobile communication initiation is mostly unidirectional in the internet, which is from the mobiles to the fixed hosts. Now, in the name of mobility support, what we have are redundant app-specific solutions developed by several applications, such as VoIP and messaging applications, notification services, cloud storage applications, and so on. Now, how many times have you faced this problem? You're downloading a large file from a web server, and you need to leave for somewhere. And you think, OK, should I let this download complete and then leave? Or should I leave now and restart the download all over again later? Similarly, popular VoIP applications sometimes drop calls instead of seamlessly switching from Wi-Fi to cellular. Now, the root cause of these problems is that communication on the internet happens based on IP addresses, which keep changing due to mobility. Now, what does not change is the name or the identity of who we are communicating with. Thus, if we can enable communication over names, we can address mobility. Now, a global name service enables name-based communication by keeping an up-to-date mapping from name to network addresses for all names. Now, given the usefulness of GNS, or global name service, in handling mobility, we state the goal for designing it as follows. So we seek to design a massively scalable geo-distributed global name service to enable secure name-based communication. It should allow us to communicate with a flexible set of endpoint principles, such as interfaces, devices, services, content, and so on. And it should not restrict how these endpoint principles choose names. It could be a hierarchical name like today's DNS, or a flat self-certifying identifier, or other application desired formats. Now, the challenge here. Yeah.
At some point, are you going to discuss industrial and other proposals to solve this problem, like Lisp, which Cisco is big on? Are you going to describe why you're sort of revisiting this problem?
There's been 3 different ways to handle this problem, and one of the ways is the name service approach. In fact, this particular approach has also been proposed. We are going to see why we need a new design for a naming system, and that I'll discuss in the later part of the talk. Okay. So besides the naming approach, there's other approaches that have been proposed. But we believe that a naming service approach is preferable to these other approaches. And I'll refer you to the paper if you're interested in that question. I will discuss why we need a new naming service design in the talk. And the challenge is to handle the update load which mobility creates. And imagine the scale of 10 billion devices that are changing their addresses at the rate of 100 times per day. And that's an average load of 1 million updates per second. So now, in achieving this goal, we make 2 main contributions. First is a clean slate naming system design that has support for arbitrary names and has a decentralized root of trust. Now, neither of these are satisfied by today's naming system DNS. And next is a scalable service for mapping names to network addresses that provides small latency for name to address mappings under high mobility. And the service is deployable in DNS today. So let's start with the naming system design. Now in DNS, so the goal of security in this naming system design is to verify the identity of who we are communicating with. And in DNS, we have domain names that get mapped to IP addresses. And a set of DNSSEC extensions have been proposed to enhance DNS's security. But the problem there is that due to DNS's hierarchical design, security in DNSSEC depends on a chain of trust with a single root of trust. So how do we avoid this single root of trust problem? In fact, our problem is more general in that we are seeking to map arbitrary names to IP addresses, and not just hierarchical names like DNS. Now our solution to this problem is to decouple the process of name certification from name resolution by introducing an additional layer of naming. And this additional layer is a self-certifying globally unique identifier, or a GUID. And by that I mean it's the public key of the name owner. We propose the use of name certification services to map an arbitrary name that bind an arbitrary name to its self-certifying GUID and the identity of the GNS provider. Now this GNS provider will then map the GUID to current set of IP addresses. So this split allows multiple name certification services to exist, thereby resolving the single root of trust problem. But there's two additional issues. First is, how do you know which arbitrary name maps to a particular name certification service? And to that end, we propose the use of certificate services that index certificates from various NCSs. And next, the next question is, how do we verify the identity of this self-certifying GUID? Now this isn't really a problem because an endpoint principal whose name is a self-certifying GUID can authenticate its identity to anyone without requiring any NCS or name certification service. Now the design is also more flexible than DNS because it allows for arbitrary names. And moreover, the GNS provider design can itself map names to network addresses that are represented in any format. And of course, it can map domain names to IP addresses. So this can be deployed in DNS today as a scalable authoritative name service provider. And in the next part of the talk, I'm going to talk about the design of this system Auspice. And the key challenge that this system addresses is to provide small name lookup latency under high mobility. So why is this challenge? This challenge is there because there's a cost of replicating these name records. So let's say we have this rectangle which represents the total capacity we have of all servers. Now a part of this capacity would be used in handling name to address lookups from the clients. So that's the lookup cost. Now another part of this cost is the update cost for maintaining the consistency of the name records that are stored in the system, because these are getting updated by the clients. Now in fact, the more the number of replicas of the name record that we maintain, this update cost increases. Now in general, when you consider a name in the system, its update cost depends on the number of active replicas as well as the rate at which the name is updated. And this is what creates a trade-off between the update cost and the latency of name lookups. And simple schemes, replication schemes, do not achieve a good trade-off. For example, a scheme such as replicate at all locations, that scheme can potentially reduce the lookup latency if there's enough system capacity, but it's still a poor choice because of the high update cost. On the other hand, a consistent hashing-based scheme, which is another well-known scheme, with a few statically chosen replica locations. Now this scheme can potentially would reduce the update cost, but it's bad in terms of lookup latencies because these replicas are placed at randomly selected locations and not close to regions of demand. Now we want this particular system to achieve a much better trade-off. So when resources are small, so that you can only create few replicas, we still want the system to give a lower latency, lookup latency. But when more resources are available, we want the system to use these resources to further reduce lookup latency. So our system does achieve this favorable trade-off using a demand-aware placement approach. And the number of replicas in this approach is chosen proportional to the lookup rate. That is, which means that the more popular a name, the greater the number of replicas, and inversely proportional to the update rate, which reduces the update cost for names that have a high update rate. And the proportionality constant there is chosen based on the system load. Now, what about the locations of these replicas? So let's say these 10 are our geo-distributed servers. And we have a name I, which is popular in the regions shown by the blue circle, and another name J, which is popular in the regions shown by the yellow. So we place the replicas of a name in a geolocality-aware manner close to regions of demand. But this approach alone is not enough because it can sometimes create load hotspots. For example, if we repeat the same process with the name J, it creates a load hotspot on one of the servers. Therefore, Auspice places a fraction of these replicas randomly to trade off locality and load balance. Now, there's one more important component of the system, which is the component that actually implements this demand-aware placement approach, and that is the placement engine. So to understand this, let's assume S1 to S10 are the different servers that we have. So the role of the placement engine for a name is given to a fixed subset of these servers. So we use consistent hashing based on the name to select this fixed subset of servers, and those servers act as the placement engine for this name. And the job of these placement engine servers is to select then the active replicas, which actually store the name record. So let's say these 4 servers are chosen as the active replicas. And these active replicas, in order to help the placement engine make these decisions, they report the geo-distribution of demand back to the placement engine. And if, again, the demand geo-distribution changes, the placement can get updated. Now, this is a distributed system operating in an asynchronous environment, so consistency guarantees are important. And the placement engine provides a strong consistency guarantee by providing a total ordering of rights to name to a total ordering of rights. And the active replicas they have an option of, in this design, they can provide flexible consistency, choosing between a less expensive eventual consistency and more expensive total ordering of rights for a particular name.
So this sounds neat. I guess, doesn't the lesson from the first part of the talk, as in why doesn't something simpler work here? In that, if you think about names, most likely they'll have a Zipfian distribution in terms of popularity, in which case if it's a 95.5, you just replicate the 5% active everywhere and the 95% nowhere, as in at one location. Would that suffice?
So what we're talking about here are, first of all, the Zipfian distribution itself. We're talking about names of individual mobile entities. And so a particular name may not be that popular. It's possible that most of them are very unpopular. Okay, so
that leads to another question. In the case of mobile entities, won't the distribution be almost a flat line?
Yeah, probably. Yeah.
In which case, why the demand aware doesn't, because if
so the aggregate request rate may be similar, but the geo-distribution of demand for a particular name may still be different and can still be exploited. So the total demand, by that I mean the number of requests that come, that may be the same, but the geo-distribution can still be exploited.
And do you have evidence of that?
So this service doesn't exist today. So it's hard to get evidence. But we can still surmise that, if a large fraction of people that you communicate with maybe from one country or 2 countries. So there's evidence that you can have geo-distribution. So that is actually a difficult evaluation challenge that we have in our system. And this experiment demonstrates that some of the simple schemes that we considered before, as well as DHT-based scheme, do not achieve the same trade-offs as Auspice. So the first scheme is replicate at all locations. And that scheme actually can sustain a very small request load because it quickly uses all its capacity in processing writes at all locations. So the moment the load increases a little, it exhausts its capacity and the lookup latency just shoots up. So x-axis is the request load, y-axis is the lookup latency. Now the next scheme is random k, which makes 3 replicas of a name at randomly chosen locations. And the third scheme is a DHT-based design that's proposed for DNS. So somewhat surprisingly, we see that the random k scheme actually performs better than the DHT-based design. And this difference occurs because of difference in redirection policies. So DHT sends a request to a replica selected using DHT-based routing, which is often not the closest one, but the random case sends a request to the closest of the 3 replicas, which is why the random K does better. But the real gains that we see are from Auspice, which places these replicas more intelligently close to regions of demand. And as the load increases, what we see that, and the other difference is that Auspice can also sustain a high request load. So unlike replicate., which quickly fizzles out, and whose latency initially is actually pretty good, but then it can't sustain a high request load, Auspice reduces the number of replicas as load increases, which also enables it to sustain a higher request load as well. So the takeaway here is that static placement like replicate et al. Or random K, as well as DHT-based design, do not achieve the same trade-offs as Auspice. And next we compared Auspice against the state-of-the-art authoritative name services that are there in DNS today. And these are called managed DNS providers. One such provider is Ultra DNS, and which has 16 known data center locations. Yes?
In the previous experiment, where is the demand coming from? So do you generate kind of random demand?
Sorry, I should talk about that question, yes. So we didn't have a real-world workload. So this is a synthetic workload. And the demand for a name, so we defined a geolocality metric, which allowed us to play with it. So the geolocality metric essentially is that 75% of the requests are coming from 10% of the location, and the rest 25% are distributed randomly. So that's the geo-distribution question. There's other aspects of the workload, read-to-write ratios. But okay.
And did you explore kind of,
Yeah. So we have a sensitivity analysis of those in the paper. Of course, the system does better when there's more geolocality. When there's no geolocality, even then it does better than something like random K, because it can choose the number of replicas more intelligently in that case.
Most of the other endpoints that need to know where my mobile phone is are going to be services that run in the cloud somewhere, right? Why don't you just let each service manage its own naming of the endpoints that need to talk to it, and it can even be in the same data center? Do you really need a global naming thing for this?
Yeah, that is the central argument. We do need a naming service because each service today is solving this problem redundantly for themselves, in that it needs to maintain an infrastructure which maintains persistent connections to all these phones to know where they are. What we are saying is that we can provide a different service, a common infrastructure service which all services can then use to know where the mobile endpoint is, and that can allow them to communicate with mobile endpoints. So we are trying to abstract out a common functionality which different services are implementing today.
Do you imagine this functionality running as a single internet-wide service, or could you just replicate the code at each of these web services?
There would be benefits for statistical multiplexing which you would get by running it as a centralized service.
In terms of load, where do you expect to be like a realistic load scenario? Because it seems that the more you go towards the right, the less is the benefit of your solution compared to random.
So the load really is relative to the overall system capacity. Actually, the last point after that, both this random K and the Auspice, both of them shoot up. So that really is the load limit. I mean, you don't have any more system capacity after that last point. Okay, so this is the comparison with a managed DNS provider. So first we measured Ultra DNS's performance for its customer domain names from many Planet Lab locations. And then we deployed Auspice on Planet Lab, but restricted it to create only 5, 10, or 15 replicas. Now the y-axis here shows the distribution of lookup latencies for different names. And x-axis shows the results for various experiments. So what we see is that with 1/3 the number of replicas as Ultra DNS, that is 1/3 the update cost, Auspice gives a similar median lookup latency. And when the number of replicas is similar to Ultra DNS, it gives a 60% lower median latencies. And these gains come from being able to choose the locations of these replicas in a more intelligent manner. So the takeaway from this is that Auspice reduces cost or latency over today's managed DNS providers, which use a static placement scheme such as replicate at all locations.
What tail performance? Is it
Can you explain that? Is it artifact of the implementation?
Yes, so it does seem to have a. I'm sorry, I don't have a good explanation for that. We didn't explore in detail why the tail performance is higher, but yeah, that is there. Yes, it could be. I don't have a good explanation for that right now. One difference is that Auspice is running on a shared infrastructure on Planet Lab, which is already shared by the other services. So that could play out to be a factor. So the summary of this sub-talk. So Auspice enables secure name-based communication, allows both names and their network locations to be represented arbitrarily. It has support for flexible endpoint principles. And the main differences from DNS are these. First, it decouples certification and name resolution. Second, it allows for it makes aggressive use of active replication and demand-aware placement to reduce the latency of name lookups. Okay. Yeah.
In the very first slide, you kind of, for Auspice, you kind of promised the capability of doing queries around arbitrary, let's say, in your case, lat long and stuff. But in the architecture, the way that you do the mapping from the consistent mapping, it doesn't seem a very easy problem to solve. So how do you approach such queries?
So something like a lat long is a much more sophisticated query to make to a name service. So the system that we have, it does provide support for storing that information, and that you can store more complex attributes like latitude, longitude. But the query pattern is not optimized yet, and the system, that's actually a future topic of which some of the other people in the group are exploring on how to enable the name service to support something like a lat long query.
But it was not only lat long, it was lat long plus radius.
Yes. So a two-dimensional query. So that is a more sophisticated query.
I think that the architecture that you have now could be extended to support those queries, or you need something very different?
You need a different service. You need a different service. But you need a global name service, I mean, a sibling of the global name service, so to say. Okay, so the overall takeaway is that content placement decisions make a lot of difference when your resources are geo-distributed. I have two pieces of news. First, the bad news. The bad news is that if you start off with a poor placement, then you can't use redirection and routing to redress the damage fully. So you have to do your placement right. The good news is that simple schemes for placement, such as LRU caching and the simple placement heuristic in Auspice, give good results. So any questions from? So with that, I'm now interested in, I'll talk a bit about some of the future work that I'm interested in doing. So until now, we had assumed that the infrastructure is dedicated to running a particular service. But in general, infrastructure is shared among multiple services. So in that case, a natural problem is to ask, OK, which are the locations that I'm going to run this particular service on? And making these decisions automatically based on, say, the pricing of computational resources at each infrastructure, the demand geo-distribution of at several locations. Moreover, we have a different cost budget for running a particular service, which may determine how many locations we can choose. And a particular service may have a particular performance requirement, which may also determine which locations to run a particular service. So automating the deployment of a geo-distributed services based on these constraints, I think it is an important problem. And solving it would simplify our management of deploying these geo-distributed services. And I believe that we can design a meta services that automates the deployment and reconfiguration of these services that can solve this problem as a common task for all these services. However, the challenge, it's not a simple problem because there may be a cost to creating a new deployment locations for a service, including the cost of data movement, the cost of moving VM images, and so on. And moreover, a service today is very complex. It may have several interconnected components. So the placement for a particular component may restrict where other components are placed. But I think doing this in an automated fashion would simplify how we deploy geo-distributed services. So that's one question I'm interested in. So people are talking about running computational resource general purpose applications on some of these platforms. And a security risk associated with doing so is that if your in-network devices run untrusted applications, and if these applications misbehave, then they could degrade performance for a wide range of users. For example, by flooding the network with packets. So how do we design a software platform that enables these applications to be useful, but restricts the misbehavior that they can cause? A third topic which I'm currently working on, and I'm interested in future, is the energy efficiency of our computing infrastructure. Currently, I'm working on a system for a particular class of data centers, which is a content data center. And we are looking at ways to reduce the energy use of servers and switches by turning a fraction of them off. And the key novelty here in the system is that it allows an operator to say, OK, this is the level of performance that I want. Now, you can save the maximum energy that you can do, but under this constraint. So determining the right point of operating in this energy performance trade-off is the problem that this particular work is solving. A natural next step would be to look at the problem of global energy management of data centers. Now, you can play around with more variables here. You can exploit the prices of electricity between different locations, or even turn off some of the data centers to further reduce operational costs like cooling. But doing so could degrade performance for users because it could increase network latency, increase network loss by sending over a different path. So what we need is a system that uses available information from a network information plane to make these decisions. Now, some of these ideas have been explored via theoretical analysis and simulations, but designing distributed systems that do this for real is an interesting research challenge. OK, with that, I'm concluding, and I'm happy to take more questions.
We had a few questions. OK, go ahead. Yeah?
OK, so if I got it right, you said that if I use LRU by caching for placement, that's a strategy that works well, yeah? So I'm kind of missing the insight there, because I would expect the kind of content you're talking about to be to sort of follow a power law distribution, in which case LRU doesn't perform well at all. Because
follow what type of distribution?
Power law.
Power
of access, right? So you have some content that is accessed a lot, and a lot in the tail that is rarely accessed. So if you have that and you use LRU, my intuition is that that's not going to work well at all. So I don't know. Could you elaborate a bit on?
I have the opposite intuition, which is that it is for the LRU Zipf popularity distribution, where most of the requests are for a small fraction of content, that you can still have a small resources and still get most of the cache hit rates that you can achieve. You do exploit one thing is if you have a few content which are very popular, then most of your cache hit rates will be derived from that the most popular content. The tail of the content doesn't contribute to cache hit rate.
Only if you start there statically, because if you have a lot of requests for things that are rarely accessed, they're going to kick out the stuff. So if they come fast enough, they're going to end up leaving no room for the content that you can get more hits of. We can take this offline though.
So I would say that the amount of so first of all, the results are for real traces, and we haven't significantly over-provisioned LRU at all. So the total amount of storage that we provisioned is essentially just twice the size of content that's accessed on a typical day. I mean, twice the size of unique content that's accessed. So your replication is essentially 2 in the system. So we aren't over-provisioning LRU, and these results are for the actual traces. Okay. Although I would agree with one question. I mean, as the workload becomes less and less skewed, the more flat it becomes, the worse is the performance of LRU. Yeah.
Hitas?
So how sophisticated is the Auspice deployment on Planet Lab? As in, does it include all the mechanisms like self-certifying certificates, and all the mechanisms that you mentioned are implemented and deployed on Planet Lab? And can we use it?
There is a portal which you can create a GUID and make simple operations. Though that deployment is not on Planet Lab, that is on EC2. We did deployment on Planet Lab for 100 locations, and it did use it did perform all the operations. For the name certification, we have a simple name email-based verification service where you can create a GUID which maps your email address to a particular GUID. And the name service does do the crypto operations and all that.
The crypto trick, by the way, is that new? Because the SFS trick was also used in like the donor work by Wolfish, right? So the security trick, is that actually new?
The security trick there is so the use of just the self-certifying GUIDs is not new, but I don't remember seeing a paper where it has been said that doing so decouples name certification and resolution and solves the single root of trust problem in DNS. This observation, I think, is new. I haven't seen that in any prior work.
Any more questions for Abigail? If not, let's thank him again.
Thank you all for coming.